This video is about trigonometric functions, and we're going to be evaluating trig functions like sine, cosine, and tangent for any angle on the coordinate plane. So not just talking about acute angles inside of right triangles, but moving out of acute triangles and going into other quadrants of the coordinate plane. So you're going to find it helpful to memorize the key degree radian equivalencies from the first quadrant, because I'm going to be using degrees and radians sort of interchangeably. So I might ask you to find the sine of 45, or I might ask you to find the sine of pi over 4, and I want you to be equally comfortable doing both. So you want to just remember that 0 degrees is the same as 0 radians. 360 degrees would be 2 pi radians, which puts pi over here. Half of pi would be like 90 degrees, and then 3 pi over 2 is 270 degrees. And then in the first quadrant, you should remember that pi over 4, of course, is half of pi, and that's equivalent to 45 degrees. So it's basically 180 degrees over 4. Since pi radians and 180 degrees are equivalent, you can always replace pi radians with 180 degrees and convert quickly in your head. Pi over 3 is going to be another really important one to know, because that's 60 degrees, and that's a really common one. And then pi over 6, you think about that as 180 divided by 6, that's 30 degrees. And of course the 30, the 45, and the 60 should look familiar to you. It's going to be really important that you know where those angles are, and then of course that you know the shortcuts for the 30, 60, 90, and 45, 45, 90. So if I use pi over 3, you should know that that's 60 degrees. If I use pi over 4, know that that's 45 degrees. And then of course I'm going to be giving you multiples of these as well, like 2 pi over 4 or 3 pi over 4. And you can base it all on knowing what 1 pi over 4 is. So really helpful to have these ones more or less memorized. I'm giving you here 3 basic trig functions to evaluate without a calculator. So the first thing you want to establish is, what angle am I talking about? When I say find me the cosine of pi over 3, if you need to convert still, then do a quick conversion if you don't have those equivalencies memorized yet. As soon as you have it memorized, you should be immediately thinking, this is a cosine of a 60-degree angle, so I'm going to draw a 30, 60, 90 triangle. Once you've drawn the 30, 60, 90 triangle, label it quickly with the sides and the ratios that you know them to be in. I like to put the shortest side as 1, which means it's across from the 30, which puts the hypotenuse at 2 and the longer leg at root 3. And then I just evaluate the trig function that I'm asked to find. So here it's asking for cosine of 60. So I go to my 60-degree angle, I'm looking for adjacent over hypotenuse, and that equals 1/2. For the next one, it's tangent of pi over 6. I should recognize that that's asking me for the tan of 30 degrees. Draw a quick 30, 60, 90 triangle. I already have one drawn, but I'll draw a second one since I wrote all over it. Relabel 1 across from the 30, 2 as the hypotenuse, root 3 as the longer leg. Find your 30-degree angle, and tangent is going to be opposite over adjacent. But of course, we're not allowed to leave an answer with an irrational number in the denominator, so we rationalize that to be root 3 over 3. And sine of pi over 4, you should recognize as the sine of 45 degrees. So you're going to draw a 45, 45, 90 triangle, labeled with the shortcuts 1 and 1 on the legs, root 2 as the hypotenuse, and then find your 45-degree angle. You can use either one and do opposite over hypotenuse. You'll get 1 over root 2, which needs to be rationalized. So just get in the habit of doing these as fast as you can. Recognize the angle you have, draw the important triangle, label it, and then find your trig function. I'm going to ask you to do so many without a calculator, and the only ones I expect you to do without a calculator are the 30s, the 60s, and the 45s. So you want to really be efficient and fast at doing these, so that then we can leave the first quadrant and do 30, 60, and 45 angles in other quadrants. So let's start to see what that looks like. Because we want to leave the first quadrant, we're going to redefine sine, cos, and tan a little bit. It's basically the same thing as SOHCAHTOA here. But if you think about having a theta, let's put theta in the first quadrant for now. If you think about having a theta, if I wanted you to get the sine of theta here and set it up, you'd want to have a triangle. So you'd create this right triangle, and you'd want to find the opposite and the hypotenuse, right? Because sine of theta would be opposite over hypotenuse. Instead of referring to these as opposite and hypotenuse, these new definitions over here refer to them as y for the opposite length. And hopefully it makes sense to you why we would call this length a y value. It's a vertical length on the coordinate plane. Anything that's a horizontal length on the coordinate plane, we would call x, which is why you'll see in the cosine definition, instead of calling it the adjacent side now, they're going to call it x. And then instead of calling this the hypotenuse, we call it r, which comes from radius. And the reason we use radius instead of hypotenuse is because the very next thing I'm going to do is leave the first quadrant by continuing to spin this terminal side of the angle into another quadrant. And I could keep spinning that around as if it was the radius of a circle. So you can put that hypotenuse really in any quadrant, and it's not going to technically be part of a right triangle anymore. So we don't want to necessarily always think in terms of opposite, adjacent, and hypotenuse. When we're on the coordinate plane, it's more accurate to think in terms of y and x and the radius. Effectively, you can still use SOHCAHTOA, so you don't have to forget that opposite and hypotenuse and adjacent relationship that you know. And that's, as you'll see on the next slide, pretty much how I do it anyway. But these are good definitions to have, and in case you ever see them in higher levels of math, you're going to want to be familiar with these definitions, the sine, cos, and tan. Of course, then if you're doing cosecant, secant, or cotangent, it's going to be the reciprocals of these. So r over y, r over x, and x over y. So how are we going to get to the sine of an angle that's outside of the first quadrant? If you write down these 3 steps, and then we'll follow them to figure out the sine of 330 degrees. So I'm going to jump right into this example. You may want to pause and write down the steps first, and then watch the example. So the first step, it says, is to sketch the angle on the coordinate plane. So we need to know where a 330 degree angle is. We know a full circle is 360, so this is just shy of 360. To be specific, it's 30 degrees short of a full circle. I'm going to then use that angle, that 330 degree angle I just drew, to create a triangle, a right triangle, that has one leg on the x-axis. And that's important, that when you draw the right triangle here, you have 2 options. You can draw the right triangle like this, or you can draw the right triangle like this. The correct one is the red triangle. The incorrect one is the green. If you look at the green, that has a leg on the y-axis. That triangle is not going to help us. Can't use the definitions that we just created for that triangle. So we want to draw the red triangle. Has a leg on the x-axis, and then the y distance is just kind of floating there in the quadrant. And of course, the right angle is between the vertical and the horizontal. So why would I want to do a right triangle? Because I'm asked to find sine, and I'm really good at finding sine from a right triangle. I know that sine is opposite over hypotenuse. So even though a 330 degree angle can't be inside of a right triangle, we can use this thing in here, which is called a reference angle. So the 330 is this angle. The 30 degrees that's left remaining is called a reference angle. And that reference angle is going to help us get the sine of 330, because we can get the sine of 30. And then it's going to end up being equal to the sine of 330, as long as we've taken into consideration what quadrant we're in when we label this triangle. So how do we take into consideration the fact that the 30, 60, 90 triangle we just created is not in quadrant 1 anymore? And here's how. When we label the sides of this triangle, across from the 30 degrees, we would always put the 1. But because we're in the 4th quadrant, that 1 is going to have a negative in front of it. It's a y value in the 4th quadrant, meaning it's below the axis. We know that down here we have negative y values, or negative vertical distance. So that negative compensates for the fact that we're not just in the 1st quadrant anymore, and then that lets us get sine, cosine, and tangent the same way we always have. The square root of 3 is positive because the x values to the right of 0 are positive. The hypotenuse is going to be 2, and never ever is negative. You never have a negative hypotenuse. If you were to think about doing Pythagorean theorem here, the very first thing you would do is a squared plus b squared to get the hypotenuse. And when you square distances, they always come out positive anyway. So our hypotenuse is positive, or our radius, I should say, is positive. Okay, and now we're ready to do step 3, which is evaluate the trig function of the reference angle. So we're going to evaluate the sine of 30 degrees in this quadrant, and that's going to be opposite over hypotenuse, so -1 over 2. And that's the final answer. So the hard work is really in drawing the triangle correctly and making sure that you've got any negatives that need to be labeled correctly, so that when you do the sine or the cosine or the tangent of your reference angle, you've got the negatives worked in where they need to be. Because of course the sine of 30 degrees is not negative, but the sine of 330 degrees is. And so that's how it compensates for the fact that we've left the first quadrant. So to define reference angle, since we used it on the previous slide without defining it, a reference angle is the acute angle between the terminal side of the given angle and the x-axis. So as shown with that, let me just sketch down here. When we had 330 degrees, which was this, right, the reference angle was the acute angle in between the terminal side and the x-axis, right? Now, it's not always going to be found by subtracting from 360. It depends on what quadrant you're in. So something like find the reference angle, we call it theta prime, when theta is 5 pi over 3. I'm doing example A here. Well, first you want to locate 5 pi over 3 because it matters what quadrant you're in. So 5 pi over 3, I can think about that as going 6 pi over 3, which would be a full circle. Only it's a little bit less than that. It's a single pi over 3 less than a full circle. And pi over 3 I know is 60 degrees. So if I'm going 60 degrees less than a full circle, I'm about here if I've traveled this way, right? 60 degrees less than a full circle. Well, the reference angle here is going to be between the terminal side, which is the blue arrow I just drew, and the x-axis, the fastest way to the x-axis. It's got to be an acute angle. So that means this is going to be my reference angle in here, the one I just traced over in blue. So to figure it out, I know a full circle would be 2 pi, and I've traveled 5 pi over 3. So it stands to reason that this must be the extra pi over 3 to get me to the full circle. So the reference angle for 5 pi over 3 is in fact just pi over 3. You can think about it as converting to degrees if you want, but I'm going to avoid doing that because I want you to start thinking in radians as well. The next one's in degrees, negative 130 degree angle. I want to locate that first. It's going to be heading in the clockwise direction because it's negative, and it puts me about here in the third quadrant when I've traveled this way to get it. Now the acute angle, which I'm trying to find, between that terminal side and the x-axis this time is over here. I'm going to trace over in blue. So I'm looking for that length, or that degree measurement. If I traveled 130 this way, and I know that this is 180, then my reference angle here is going to be 50 degrees. So when doing reference angles, just draw it, locate it in the right quadrant, and then figure out the fastest way to get to the x-axis from there, or the acute way to get to the x-axis from there, and that'll be your reference angle. Quadrantal angles are ones that lie directly on the x or y axis, and they have a little bit of a different set of rules to follow because you're not going to be able to put those inside of a, you're not going to really have a reference angle for those. You're not going to be able to create a triangle for those to the x-axis. Let's see if I can come up with an example here. Okay, what's going to be helpful to know here is the unit circle has a radius of 1, as we know. That's what unit circle means, right? And if the radius of this circle is 1, it's going to be helpful to know the coordinates of the points here at each of these quadrantal angles. So the coordinates of this point, think about it as x comma y. If the radius is 1, it makes sense that the x value here is 1. The y value is 0 because we haven't left the axis at all. Up here it has an x value of 0, but a y value of 1. Over here to the left we have an x value of negative 1 because we've gone in the negative direction. And we've not left the axis, so the y is 0. And here we're at 0, negative 1. The reason these coordinates are helpful are if I ask you to do something like the sine of 90 degrees. So before now we've only done acute angles. Or now we've done multiples of those acute angles, like 3 pi over 4, would be like a pi over 4 angle, but times 3. So we've never done the sine of a 90 degree angle before. And you are not going to be able to get it by drawing a triangle. So this is the only trig you're not going to be able to get by drawing a triangle. When you have to do the sine of 90 degrees, it's going to be really helpful to use these definitions that we wrote down. Y divided by the radius, x divided by the radius, y divided by x. using the unit circle that's drawn up here. So if you think about sine of 90 and you go to your definition of sine and it says do y at that point divided by the radius at that point, go to a 90-degree angle, which you know is up here, find the y value at that point, and find what the radius of the circle is at that point, and create a fraction. So the y value there is 1. The radius of the circle is always 1, and it's never negative. And then that just reduces to 1. So it turns out that the sine of 90 degrees is 1. You can use these definitions for any quadrantal angle. So maybe I want you to get the tangent of 270 degrees. Find the angle. 270 is here. I'm asking for tangent, so you want to find a y value and divide it by an x value. The y value is -1 there. The x value is 0 there. Well, -1 divided by 0 is undefined. And that's what the tangent of 270 is. It's an undefined value. These answers will always come out to be either 1, 0, -1, or undefined. Because if you look at the fractions that you'll be creating, it's always going to be some combination of 1, -1, and 0, right? Being divided in a fraction. I can explain this further and how it relates to the triangles that we've been doing. But for now, just use these definitions, use these formulas, and use the unit circle as soon as you recognize that you're on one of the quadrantal angles. Quadrantal angles, in case you haven't figured that out by now, are 0 degrees, 90 degrees, 180 degrees, 270, and of course 360. And then any coterminal angle with those, which in radians would be 0, pi over 2, pi, and 3 pi over 2, and of course 2 pi. So to put it all together, we can evaluate some trig functions. I'm not going to walk through all of these just in the interest of time, but just to set them up, of course the first step is to draw the angle, so figuring out where a -240 degree angle would be. It's going to be approximately here. And then you want to create, I'm going to get rid of that directional arrow, because it's just going to get in the way. So it's approximately here. And of course you want to create the reference triangle that goes straight to the x-axis and has a leg on the x-axis. Because we went around 240 degrees, and we know that the x-axis is at 180 degrees, that means I know that the 60 degrees is my reference angle, and label your triangle accordingly. Across from the 30 is a 1, across from the 60 is a √3, the hypotenuse is a 2. Check if anything needs to be negative, which here it does, and then find your tangent. I'm not going to finish that one, just in the interest of time. 17 pi over 6, we're looking for where that angle is. I know pi over 6, I know that's a 30 degree angle. If I were to think about 18 pi over 6, that would be like going 3 pi. So this is a little bit less than 3 pi. It's 30 degrees less than 3 pi. Or you can convert it if you need to. You can't figure out where 30 degrees less than 3 pi is. So I know that that's going to be just about here when I end up at 17 pi over 6. And then, of course, I create my reference triangle. 30 degrees is my reference angle, because pi over 6 is 30 degrees, and that's the amount that I have left over. And then we just label the sides across from the 30, across from the 60, and the hypotenuse. Check if anything needs to be negative in this quadrant, and then find the sine of the reference angle. And that is all.